Now I'll start the video after I sit there. Yeah, this is gonna suck. Anyway, real headache in class today, but fortunately at the very end, it will lead us into our next topic, which is the Higgs mechanism. So we're going to learn the essential lesson of why the Higgs mechanism was even proposed through our analysis today. And, you know, we're going to have some nitty-gritty detail. Try and follow it the best you can, but there is going to be sort of a narrative behind it all. So you should understand at the end of the day what the issues are and how the Higgs mechanism, or what we're going to need the Higgs mechanism to do. Okay, are there any questions before we get going? This could be a long one, so I just want to go ahead and get started. Okay, the weak interactions. These are what we're going to talk about today. The weak interactions have several characteristics which set them apart from the other interactions. The first quality of the weak interactions is that it impacts every single matter particle. Let me ask you, Jared, which particles does the electromagnetic interactions impact? Charged particles, and there are neutral particles, the neutrinos, okay? Quarks are charged, they're electrically charged, we'll learn about that later. And we have 3 charged leptons, but we also have 3 non-charged leptons. What about the strong interaction? Shaylee, what particles do the strong interactions impact? Say it again?
Massive particles? I don't know.
So the particles include the leptons, which are the electron, the electron, the electron neutrino, the tau neutrino, and the muon neutrino. And then there's the quarks, up, down, strange, charm, top, bottom. So there's 12 particles. Which of those particles do you think experience the color interactions, strong color interactions?
Oh,
The quarks, yeah. Maybe it was me saying strong versus quantum chromodynamics, but yeah, so notice electromagnetism only affects a handful of particles. QCD, the strong interactions, only affects a handful of particles. The weak interaction, that's what's so damn funny about it. It's called the weak interaction. It affects them all. That's what's so weak about it. Not. Okay. Second interesting quality of the weak interactions. The force particles are massive. Okay? So, wait a minute, hold on. The photon is the electromagnetic force particle. Is it massive? No, it's massless. The gluons are the force particles for the strong interaction. And even though I didn't talk about it last time, they are massless as well, okay? And again, the argument is that the Lagrangian for the mass, for the force particles is the Procol-Lagrangian. And the mass term in the Procol-Lagrangian breaks whatever symmetry you're trying to impose. So the only way the symmetry could be true is if the force particles are massless, okay? But for the weak interactions, the force particles are actually massive. It violates a bunch of symmetries. It violates parity, charge conjugation, and the combination of those, CP, charge conjugation and parity. And perhaps most importantly, the weak interactions can change the flavor, i.e. particle type. Okay? That is, we can start off with an electron, and that through the weak interactions, it can turn into an electron neutrino, okay, with some other stuff in the game. But the importance of that is that this is what leads to decays. Because when we talk about decays, we're talking about particles which are there, and then they go away by turning into lighter weight particles. So you actually change which particles are there when you have a decay process. The weak interactions are the only thing that can do that. Okay? All right. These are 4 really interesting aspects of the weak interactions. But by no means is any of them as important as the fact that the weak interactions are not based on a symmetry of the standard model. Wait a minute. I was blowing smoke up your nose over the last couple of lectures where I was claiming that every interaction in the standard model comes from a symmetry principle, right? You start with a global symmetry, and then you basically localize it, and that gives rise to the interactions, okay? We did electromagnetism, we did the strong interaction. Both of those stories worked out. I would now argue to you that the weak interactions do not represent a symmetry of the standard model. Does that suck? Does it follow that same story? But it turns out that there's a little bit of conditions that I have to say. Right now, at room temperatures, the weak interactions do not express a symmetry. However, earlier in the universe, or at high temperatures, or high energies, there is a symmetry underlying the weak interaction. Okay? So we have a symmetry at some scale, energy scale basically. Back in the early universe is a high energy scale as well. We have a symmetry argument, but now we don't. The symmetry there had to disappear. That's something called the Higgs mechanism, which we're going to talk about next time, okay? But that's going to play an incredibly important role in the elimination of this symmetry. Yes?
Are the symmetries of the strong interactions and the electromagnetic depend on any type of temperature or anything, or they just...
No, actually electromagnetic will in just a moment, but the strong interactions don't. Okay, everything depends on the energy scale. That's a topic called renormalization, which we'll learn later on. But the symmetry underlying the strong interaction seems to go to high energies. Features of it will change as you change the energy scale, but the symmetry is still good. But just wait on electromagnetism, because that's going to be part of this story. Okay? Okay, so here's what we're going to do. Since the weak interactions start out at a symmetric thing at high energies, we're going to go ahead and approach this at the high energy level so we can use our symmetry argument, the same symmetry argument we use for electromagnetism and strong interaction. And we'll just formulate what it looks like. Then, when we bring in the Higgs mechanism, we'll figure out how that symmetry is broken and the result, and so forth. Okay? Oh wait, there's something else amazing. This is such an awesome topic. Turns out that if you want the weak interactions to be the result of some symmetry at higher energies, the weak interactions have to be unified with the electromagnetic interactions in a very non-trivial way. And we're going to talk about that today, okay? So, what the hell do I mean when I say ElectroWeak unification? That is the unified force of electromagnetism and the weak interactions. Let me just make sure there wasn't something else I wanted to say. Yeah. Okay, so ElectroWeak unification. So we're just going to forget about the weak interactions by themselves, and we're going to talk about ElectroWeak unification. Okay, now, many of you have heard it. I've probably said it, but I just want to be more careful. It is often said that the symmetry group of the standard model is SU3 cross SU2 cross U1, okay? Where, when we look at this, as we've already gone over, electromagnetism is built on localizing the U1 transformation, so we might say that that's E&M. And then SU3 is a symmetry group underlying quantum chromodynamics, so this is the strong interactions, okay? That leaves as a natural candidate for the weak interactions this right here. Okay? Makes sense, right? Okay. This is crap. Any questions? Okay. So this is actually the correct group. Questions? Oh, I forgot a couple of things. Okay. We're going to talk about what that L means, and we're going to talk about what that Y means. But this is the high energy group structure which underlies all of the standard model. This is the underlying group for quantum chromodynamics as we expected. This is the underlying group structure for the ElectroWeak interactions. Okay? When we go to low energies, like a room temperature, this gets broken into SU3 cross U1, where this is the electromagnetic U1, okay? So again, we have QCD and then QED. So in order to figure out the weak interactions, we have to start with this ElectroWeak unified group. And then the Higgs part of the story will tell us how it gets down to here, okay? So we don't need to worry about QCD in today's talk because, you know, this is just a completely independent thing, all right? So we're really going to focus on SU2L cross U1Y. All right? Now, PJ. Sergio. What do you think the L means?
Left.
Yes, it means left. Good. That was a good answer. This is regards to chirality, which we'll talk about in a minute. Sean. What do you think Y stands for? Well, this is L for left. This is Y for hypercharge. Oh. Yeah. Awesome. It's the second letter of hypercharge. It's obviously Y. Dang, man, you guys are tearing it up today. No, I'm just kidding. Okay, so the L here stands for left-handed fermion states. Wait, what is a left-handed fermion state? What do you think left-handed means? Anybody?
Is it twisted in the left direction?
Well, what have I talked about over the last few lectures where I talked about the handedness?
Is it a left-handed?
Well, there's right and left-handed coordinate systems, but we're talking about particle properties. Does anybody remember my helicity story? You know, if I got a particle that's moving with some momentum p, and its spin is along p, then it's got a right-handed, and if the spin is anti to p, then it's left-handed. Do you guys kind of remember that?
Doesn't that only like matter for massless particles though?
Well, So that's the interesting thing. This notion is fine for massless or massive, but if for massive particles it can be the, okay. So let me just give you the words, and then I'm going to go back to their distinction. What I'm talking about here is helicity. It's how the spin aligns or anti-aligns with the momentum. For massless particles, it's invariant. For massive particles, you can always change the direction of the helicity, okay? And we use left-handed and right-handed to describe this. Does this make sense? We're using left hand here out of tradition. It has nothing to do with helicity. This is actually chirality, not helicity. Okay? Now, that could be a little bit confusing, so let me revisit and clarify the difference between helicity and chirality. So, if we started with a spinor psi, okay, this is just an arbitrary spinor, then we can do two different projections on it. We can do 1/2, 1 plus S, or plus minus SP on psi. And that's going to give us something which we could label with a plus minus, which corresponds to the choice there. And this is a state of definite helicity. Okay? That is, if I act on a state with definite helicity with the spin up, with this component of spin along the momentum, then I'm going to get back plus minus h bar over 2 psi helicity plus minus. So if I take an arbitrary spinor and I project it with this operator, which you built in your homework last time, then you're going to get helicity eigenstates plus or minus, which are basically the eigenstates of the spin operator, with eigenvalues plus or minus h bar over 2, okay? Alternatively, I can take this same generic spinor and I can project it with the gamma 5 matrix, okay? In this case, what you get after that projection are different states of chirality. Hence, if I act on a chiral state with the gamma 5 operator, I'm going to get plus or minus the chiral vector, the chiral spinors back. So these are eigenspinors of the gamma 5 matrix. Okay? So just notice, helicity is defined in this way with this projection operator. Chirality is defined in this way with this projection operator. Okay? There are even more differences. Okay? If I consider helicity, then helicity is not Lorentz invariant. But remember, when we talked about helicity, we said, oh, that's the spin and its alignment with the momentum. And so if you have a plus helicity state, where the spin is aligned with the momentum, you can just do a Lorentz transformation and reverse the direction of the momentum by boosting to a frame such that this motion is backwards. That doesn't change the direction of the spin. So you can do a Lorentz transformation to change the helicity to minus. Okay? So helicity is not Lorentz invariant. Chirality is. And you might say, oh, chirality wins. Well, not entirely. Whereas helicity is not Lorentz invariant, in a frame, it is unchanged. That is, if I just pick a reference frame and watch the motion of the particle and look at its helicity will not change. Okay? Whereas the chirality will change in a frame. So the chirality can actually change its value without touching the reference frame. Okay? Now here is where it can get a little confusing, but I just wanted to start out with these very different stories first, okay? If a particle has 0 mass, then helicity is basically the same as chirality. It turns out if a particle has 0 mass and you use this projection to the helicity, then you'll get an eigenstate of spin, and this will also be an eigenstate of gamma 5. I argued this in a couple lectures ago. I actually wrote down the spinner that's projected and then showed that when in the massless limit, it's an eigenspinner of both of these. Okay? So for the massless case, you have both of these properties, which of course means that the helicity becomes Lorentz invariant. But remember, we said that if you're massless, there's no way to reverse the helicity because you can't boost past the thing. Okay? Similarly, the chirality won't change for the massless case. Does this make sense? All right. Okay. So, okay, it's about to get ugly. Fasten your seatbelts, folks. A little bit ugly. It's not going to be that bad. Pretty bad. Okay, so let me go to this. All right. So recall the Dirac Lagrangian. Okay. Where we actually took this and rewrote it after our definition of chirality as minus h bar c I psi minus dagger d mu sigma mu psi minus plus I psi plus dagger d mu sigma bar mu psi plus plus mc squared psi minus dagger psi plus psi plus dagger psi minus. Okay, where the sigma mu here is I and sigma I, and the sigma bar mu is I and minus sigma I. Okay, now this was the Dirac Lagrangian written in terms of these 2 component objects. These size are 2 components. These size are 4 components, but these are 2 components. And we made the observation that if the mass is 0, then we can get rid of one of the components. We can just do psi minus if we want. Because if the mass is 0, we don't have this term. We could erase this and just be left with this. If, however, the particles are massive, then there's no way you can erase either psi plus or psi minus because they're both required for the mass term. Okay? What we'd like to do is go back to 4 component objects. Okay? So to go back to 4 component objects, what we can do is we can define a right-handed state as basically psi plus 0 and the left-handed state as 0 psi minus. So each of these are two components. So this is overall 4 components and 4 components, all right? Then of course we have that psi is psi plus psi minus, or you can always write it as psi right plus psi left. Doesn't matter. Okay? Now let's recall this is an arbitrary spinner. If we want to project on it, then we just use the good old 1/2, 1 plus or minus gamma 5. Okay, that's the chiral projection. Okay, so of course if we take this and we hit psi with it, that's an arbitrary spinner. This is going to give us back, well, first of all, the operator, if If we actually plug in what the gamma pi matrix is, it's 2, 0, 0, 0. Okay? Psi right, psi left equals psi right. Okay, so the right-handed component is simply what comes out when I use the chirality projection operator on psi. And obviously, if I use the negative component, I get psi left. Okay? Now, something interesting happens though, because this is how psi gets projected. However, let's look at psi bar. Remember, psi bar is defined as I psi dagger gamma 0. Okay, so this is what you can think of as the dual spinner, and it comes from the original spinner through this construction. All right? Now we can ask, what does the right-handed component of psi bar look like? So we'll just do this. So we're going to bar this expression right here. No, sorry, we're not going to bar this. We're going to bar P plus on psi. So I can write this as 1 plus gamma 5 over 2 times psi. Okay. This is psi right. Okay, that's just the P plus operator on psi, which gives me psi right. So, I mean, it's 1/2 1 plus gamma, or it's 1 plus gamma 5 over 2. All right? So now we can bar this according to this prescription. Okay? So this is going to be I 1 plus gamma 5 over 2 psi dagger gamma 0. Okay, again, I just take everything that's in my psi expression and I just dagger it, and then I just tack on I and a gamma 0. Okay? And now, of course, I can do the usual thing if I'm daggering a combination of things, and I reverse it if I want to do the individual daggers. So this is going to be I psi dagger 1 plus gamma 5 over 2 dagger gamma 0. Davis,
Yeah.
can you tell me what 1/2 dagger is? Well, actually, there's two questions. One is, what is 1/2 dagger, and the other one is, what is gamma 5 over 2 dagger? I'll do one if you do the other. Which one you want to do?
I like 1/2.
Really?
Yeah.
1/2's way harder. It's so complicated.
Is it
You
not
could
1/2?
try it. Yeah, it's 1/2. I'm totally kidding you. 1/2 is daggered as 1/2. Gamma 5 over 2 daggered is gamma 5 over 2. Gamma 5 dagger is gamma 5. Okay? So we can actually just erase this. It's a nice property of gamma 5. Okay? And now, oh wait, look, hold on. I psi dagger gamma 0, I psi dagger 1 plus gamma 5 over 2. Okay. Maybe I'll just move this to the other side. But when I move gamma 0 past 1/2, what happens, Henry? If I'm moving gamma 0 past the number 1/2,
Oh, none.
none. What if I move it past gamma 5?
Then you get a negative sign.
Then you get a negative, exactly. Okay? Well, this means psi bar 1 minus gamma 5 over 2. So the point of this is to get the right-handed component of the dual spinner. Instead of using 1 plus gamma 5, we use 1 minus gamma 5 on it. Okay? Okay, so with that in mind, we can go ahead and write the Dirac, the equivalent of this and this, using these left and right components. So here we go. H bar C. Actually, I'm going to write this up there. I'm going to erase this because we're not going to need it anymore. And this is all work done. All right. H bar C. psi bar right plus psi left, gamma mu d mu, psi right plus psi left, plus mc squared, psi bar right plus psi bar left, psi right plus psi left. Okay? Huh. It doesn't really share this property, right? This property you only had plus and minus combinations. Here I could have right and left and right, but I could also have right and left and left. So it doesn't, I mean, even though the right component is just psi plus 0 and the left is 0 psi minus, it seems that I've taken this where I'm saying, like, if the mass is 0, then you can take, you know, just the plus or just the minus. But if the mass is not 0, you require both. However, you know, like, it seems like I could take the left-handed parts to 0 and still have a mass term, right? Well, it turns out this contains the same information as this. Let's see. First of all, if I do psi bar right, gamma mu, psi left, okay, then this is, and I'm basically just looking at the spin space structure. D mu, that's a space-time operation. It's just the derivative with respect to where you are in space-time. Okay, so it's got a trivial spin structure. This is obviously a matrix in spin space, and then these are spinners in spin space. So I want to look at the spin space behavior. So this is going to be psi bar 1 minus gamma 5 over 2. That's just the right-handed version of psi bar. Times gamma mu 1 minus gamma 5 over 2 psi. That's the left-handed component of psi. Okay. And then I can move this past the gamma mu to combine it with this, and that's going to give me psi bar gamma mu 1 plus gamma 5 over 2, 1 minus gamma 5 over 2 times psi. Oh wait, hold on. This is psi bar gamma mu 1 minus gamma 5 squared over 4 times psi. It's just 1 plus times 1 minus. It's really simple. Joey, can you tell me what that is? What's the value of that? I'll give you a hint. It's contained in the 1 minus gamma 5 squared. Do you remember what gamma 5 squared is?
Gamma 5. Or sorry. Is it I? Can't remember.
It's 1. Okay? So it turns out that in expanding this kinetic term, mixing psi right with psi left is always going to give me 0. And similarly, psi bar left with psi right. So that means the kinetic term, well, basically in expanding this product, I'm only going to have psi bar r, psi r terms, and psi bar left, psi left terms. Similar to here, where I have minus and plus plus and no mixed terms in the derivative. Okay? Now we can consider psi right, psi bar right, psi right. So this would be a term from here. And this is once again going to be psi bar 1 minus gamma 5 over 2, 1 minus, or 1 plus gamma 5 over 2 psi. Remember, if I want the right component of psi bar, I do 1 minus gamma 5 over 2. If I want the right component of psi, I do 1 plus gamma 5 over 2. But what's this equal to? 0, same story. So that means that in the mass terms, if I'm considering the psi bar right combined with psi r, that's automatically 0. So in the mass terms, the only ones that are not 0 are psi bar right with psi left and psi bar left with psi r. Okay? So at the end of the day, our Dirac Lagrangian simplifies to h bar c, psi bar r, gamma mu, d mu, psi r, plus h bar c, psi bar left, gamma mu, d mu, psi left, plus mc squared, psi bar right, psi left, plus mc squared, psi bar left, psi right. Okay? Where everything in this expression is composed of 4 component spinors versus this 2 component story. All right? Any questions? All right. Now, it's time to try and address the symmetries. Okay. Remember, our symmetry group is SU2 left cross U1 hypercharge. Okay? First of all, let's start with the SU2 left. For SU2 left, these are obviously complex 2x2 matrices. So as such, if they're going to act on something, they have to act on something that has 2 components. And it's exactly the same story we encountered with the strong interactions. The SU3s were 3x3 complex matrices, so we had to have it act on things with 3 components. And we introduced red, blue, and green, the 3 colors. So we said every single quark, whether it's up, down, strange, trump, top, bottom, it doesn't matter. Every single quark comes in these 3 flavors. So I can say the red up quark, green down quark, and blue down quark. Or, all 3 ups, sorry. At any rate. This has to act on 2 component things. So what are we going to introduce in this story? What kind of doublets? What are they?
Up, down.
Exactly. Remember, I've been organizing all of the matter in the standard model in these little pairs. Up, down quark, charm, strange quark, top, bottom quark. Electron, electron, neutrino. Muon, muon, neutrino. Tauon, tauon, neutrino. Those are 2 component objects. Those are exactly what these 2x2 matrices enact, or act on, okay? So we can say that we have left-handed doublets, which is going to be comprised of the electron neutrino with the electron, the left-handed part of that, the muon neutrino and the muon, the left-handed part of that, the tauon neutrino and the tauon, the left-handed part of that, the up and down quarks, the left-handed part of that, the charmed and strange, the left-handed part of that, and the top and bottom, the left-handed part of that. Only the left-handed parts. Notice, everything is broken up in this Dirac Lagrangian, so this is the Lagrangian good for any matter, but it's just written in terms of left and rights. We're only going to use the left-handed parts with this doublet structure, okay? For the right-handed side, we get singlets. Okay? wait a minute, am I missing something?
My research group hopes so.
Yeah. I seem to be missing the right-handed neutrino components. In this class, which we're not going to go into as research, but in the modern take on things, you could actually have right-handed neutrinos, but that's owing to the fact that neutrinos might actually have a mass. In this story that we're going to tell in this class, we're just going to go with massless neutrinos, okay? And if you have any questions about masses, that's who you can talk to, okay? But what's important is we're going to go massless neutrinos, therefore they don't have right-handed components. They only have left-handed components, okay? Remember what I said, if you're massive, then you cannot have just left or right. You have to have both. But if you're massless, you can have just left or just right. Well, it turns out in the massless story, we only have left-handed neutrinos. We do not have right-handed neutrinos. Yes?
Sorry, this is, but when we are talking about matter, but if we talk about antimatter,
So antimatter largely follows the same story.
but we work also with, for example, left or right.
Yes.
With right or with?
Wait, ask the question again.
It's like you are taking the doublets of left of all the particles, but if you develop, okay, I will develop the same, but for antiparticles, so you should take the doublets of right, or I'm not sure.
So are you saying that we would use left-handed particles and right-handed particles, but we would use, we would use left-handed doublets of particles, but we would use right-handed doublets of antiparticles? Yes.
If you are developing if you want to develop in the case for anti.
Yes. That you'll switch.
Okay.
Yeah. Okay. Sam?
So, we're calling these XL, these doublets we're referring to,
Yeah, this is a doublet.
and the other ones are just singlets.
Singlets.
Is that accumulated as XR or no?
Well, no. I mean, this is plenty of a label. We don't have to give it another label. This is going to be. Yeah. I mean, we could just write them like this, and that'd be the end of it. We don't need this label. Okay. Yes.
So you said we were only taking the right-handed parts of the other ones because the neutrinos have no mass?
Yeah.
What about like the up quark and the?
They all have mass.
They don't have mass either?
No, they all have mass.
They all have mass?
Yes.
So why are we only taking the right-handed parts of that?
Why are we taking the right-handed parts?
Oh, sorry, never mind.
Yeah, we have all 6 quarks
Yeah,
here. Yeah, just three leptons and 6 quarks. Everything that has mass, well established, has a right-handed component. Okay? Like I said, he's got plenty of answers to all your questions about, wait a minute, those neutrinos have mass, what do I do? Okay, but let me continue because the next sheet's gonna be the big bad ugly one. Okay, so what we're gonna do for simplicity, obviously, is we're gonna focus on this and this. Okay, so we're just gonna play our story out in terms of the electron, the left electron, neutrino, electron, and then the right-handed electron. And everything that I'm gonna play out will copy itself for the rest of these, okay? All right, and we're gonna go ahead and ignore the mass term as part of this story. We'll come back to that later. But we're just basically gonna focus on this derivative term because what we wanna do is we wanna take this gauge symmetry, this SU2 left cross U1Y, and we want to gauge it. We wanna make it local, okay? And we all know that the derivative is the term where that gets screwed up, okay? So here we go. Let me just write down what the Lagrangian looks like for these terms. We're gonna have the Dirac Lagrangian takes the form H bar C, chi left bar, gamma mu, d mu, chi left, plus H bar C, E bar right, gamma mu, D mu, E right. Okay? This is just this term right here for the left, and this term right here, whoops, this term for the left, this term for the right. If we're doing the left, we have to include the doublets, and if we're doing the right, we just use the singlets. Okay? All right. Now let's go back to pseudo-familiar ground. Let's gauge this symmetry of this Lagrangian. Let's localize it. Okay? As you can expect, this is going to be ugly. All right. Okay. So, first of all, this is what is often called the isospin transformation. And I'm just giving you names, so if you want to look any of this up, you can. And this is once again given by the hypercharge. Okay? Where the SU2L transformations take the following form: e to the minus ig sigma dot theta chi L, where G is also Q over H bar C. And then the U1 hypercharge transformation takes the form e to the minus I G prime Y chi L, acting on chi L, and then e to the minus I G prime Y E R, there should be a phi parameter in there, times E R. Okay? Now, let me just go over this really quickly. First of all, U1, this hypercharge, acts on both the left and the right sides. It doesn't have to just act on one side. It acts on both. So we're having this transformation transform the left and the right-handed parts of the story. The SU2 left only transforms the left side. Okay, Sam?
Sorry, on the SU2, is that G sigma dot theta?
Yeah. Okay. So once again, we've taken this and we've broken it up into a left-hand piece, which is a doublet, a right-hand piece, which is a singlet. U1 acts on both of them. There it is. Notice U1 is just a complex number. It's not doing anything to the fact that there are two pieces in this story. It's just multiplying the whole thing by a complex number. And it's multiplying this by a complex number. SU2 left is acting on these complex doublets by a multiplication by a 2 by 2 complex matrix. And it's not touching these. Okay? All right. Now, so G is obviously the coupling. So sigma is the generators. This is the story of the exponential map. Sigma is the generators. Theta is the parameters for each generator. How many generators of SU2 are there? 7, 8, 12. SU2. That's SU3. 3. There's 3 generators of SU2. It's isomorphic to SO3. Remember? That's how we found spinners. And SO3 has 3 generators. At any rate, there are 3 generators. There's 3 sigmas. Each of them gets its own parameter. You can do this much in this generator, this much in this generator, this much in this generator. That's why we write theta as a vector of parameters. G is the coupling. Okay? Now down here, again, this is just a complex number. Phi is the parameter that we're transforming by. G prime is the coupling, but this factor of y chi left and y e right is just in case the coupling to the left is different from the coupling to the right. So I'm going to put a G prime factor in, and then I'm going to let this impact overall change between this y chi L factor and this y ER factor. So this is just saying this U1 transformation might act on the left with a certain strength and the right with a different strength. Okay? Okay. All right. Here we go. Oh boy, it's going to be a headache. So what we want to do is we want to take the ordinary derivative of the left-handed component of the story, and we want to turn it into the covariant derivative. Okay, so we're attacking this term first, and then in a few minutes we'll attack this term. So in order to do this, we should remember how the story goes. We get the ordinary derivative plus IG sigma, and then we have to introduce gauge fields, one for each generator. We have 3 generators, so we'll introduce 3 gauge fields. Okay, they are vectors in space-time. This is just like the photon or the gluons, but there are 3 of them. That's why it's a little vector. The fact that it's a space-time vector is indicated by this mu. This vector sign just says this has 3 components, this has 3 components. Okay? Times chi L. And then we also have this impacting the left-hand terms. So we have to gauge this, we have to include this in our modification of the derivative as well. So this is going to be I G prime y chi L times B mu chi L, okay? Where this is just a U1 gauge field. All right? And this, as I mentioned, is 3 SU2 left gauge fields. I should say this is hypercharge. Y. Okay? So our story automatically has 4 gauge fields, because acting on the left-hand side of this story, we have 3 from SU2 left and then 1 from this U1 hypercharge. Now we also have a derivative of the right-handed singlet. So this is going to have to be promoted as well, but this gets promoted in a simpler fashion. This is just plus I G prime y ER B mu ER. That is, we just get this term with the y ER instead of the y chi L. We don't get this term because this does not act on the right. Okay? So these are our proposed redefinitions of the derivative. And what I would argue, and Connor's going to help me, Connor, if I put this derivative and this derivative into this Lagrangian, what do I have to determine in order for this to be invariant with these derivatives in there? What unknowns do I have to determine?
You need to find the transformations
Of?
each gauge field.
That was a perfect answer. Give the man a hand. Someone's paying attention. All right, yeah, we have to plug these in, and then demanding that it be invariant, that's going to tell us how the W's and the B's transform. Okay? So as you may or may not remember, this is very similar to what we've already done with both the QCD, which has a non-abelian group like this one, and then an abelian group. Go ahead.
So the Y, ER, and Y, are those scalars? Or are they?
Yeah, those are just numbers, yeah. Okay, so you might or might not remember, but from the SU3 story, which was a non-abelian group, we found that the transformation has to be written in terms of the generators contracted with the gauge fields. That the primed version of the gauge fields goes as e to the minus I g sigma dot theta sigma dot w mu e to the I g sigma dot theta plus I over g d mu e to the minus I g sigma dot theta e to the I g sigma dot theta. Okay. And then for the gauge field for the U1, it's that simple result that it's B mu plus D mu phi. Okay? So we have here our gauge field transformation rules. Drew. Is Drew here? I don't see Drew. I had not seen Drew without a mask, ever. This is the third class you've taken from me? The third class he's taken from me, and I'd never seen him without a mask. When I saw him at colloquium, I was like, you got Drew's hair. You're Drew. Okay, Drew, what's the next step in the story?
Plug in and suffer.
Plug in and what?
Plug in and suffer.
Nope. Oh, yeah, you'd plug this in, but there's actually, without ever planning to actually plug anything in, there's another critical step to the story of localizing a symmetry in order to get an interacting theory. I mean, this will give us an interaction, but it'll give us an interaction between the spinner and a background.
Gauge field?
It'll give us the interaction between the spinner and the gauge field, but the gauge field will just be a background. It is not dynamical. What do we have to add to the story to get the gauge?
Kinetic term for the gauge field.
Yes, exactly. We have to add kinetic terms for the gauge fields, okay? So remember how you do that. You say, okay, the kinetic term for a gauge field is just minus I over the coupling times the commutator of d mu d mu, okay? Which is obviously going to be different on the left and the right. So if we do this, we'll find F mu nu equals d mu b nu minus d nu b mu for the U1 hypercharge. That's what we expect. That's the same as electromagnetism. And we're going to end up with F mu nu A, which is d mu w a nu minus d mu w a mu minus g epsilon a b c w mu b w mu c for SU2 left. Okay? This is a little bit different than in the SU3 case, because in the SU3 case, if you do the Lie algebra of SU3, you get these structure constants, these F's, and they're different values. However, SU2, that Lie algebra just uses the Levi-Civita. Okay? All right. I mean, these are the structure constants of SU2, they just happen to take that particular form. Well, wait a minute. SU2 left, kinetic term for SU2 left has the derivatives of the gauge fields. Then it has these terms. What kind of terms are those? Of what? With what?
Of the gauge fields with other gauge fields.
Exactly. Remember how for electromagnetism, the photons don't interact with other photons? But for QCD, SU3, quantum chromodynamics, we found that the gluons interact with other gluons. And we pinned that on the fact that SU3 is non-abelian. Well, guess what? SU2 is non-abelian. So the SU2 left induces interactions between the gauge bosons. Okay? But it's going to turn out to be an even more interesting part of the story. Let's follow this. We expect 3 gauge bosons, and let me go ahead and erase this. We expect 3 gauge bosons. So we'll call them W mu 1, W mu 2, W mu 3. And then we have the gauge boson for the U1 part of the story. And these gauge bosons, they act on the 2 component parts of the spinner, okay? Now, these are acting on these doublets. So, when I combine these with the generators, these are going to be 2 by 2 complex matrices. They're acting on doublets. Have we ever seen this before? 2-dimensional spinners from quantum mechanics. That's where we've seen this. In fact, the underlying group in that story was SU2. Remember, we took 3 spatial dimensions, SO3, and we said, oh, that's equivalent to SU2, therefore you can do a 2-dimensional complex spinner representation of that. Well, those same ingredients are here, even though now we're not talking about spinners. We're talking about spinners, they're a story, but they're 4-component objects. Rather, this is the 2-dimensional space of the weak interaction. This is the doublet, which has nothing to do with space-time components, but rather flavor, up, down, neutrino, electron, okay? So we're going to use the same machinery that you use in 2-dimensional spinners and non-relativistic quantum mechanics, but we're going to apply it to this space, okay? And the reason I say that is because we could imagine that W mu 3, which is related to 1/2 sigma z, okay? Well, if you just look at what sigma z is, that's 1/2, 0, 0, minus 1/2. Whereas if instead of using sigma 2 and sigma 3, so this is using, this is sigma z, yeah, okay. Instead of using sigma 1 and sigma 2, let me combine them into a linear combination, which is suggestive of what they might be able to do. Let's combine them into 1/2 sigma 1 plus I 1/2 sigma 2, and then W mu minus, which is 1/2 sigma 1 minus I 1/2 sigma 2. Hopefully you've seen this sort of manipulation in many contexts. In this case, the matrix becomes 0, 1, 0, 0, and in this case it becomes 0, 0, 1, 0. Okay? So really simple matrices from these linear combinations. And then this is obviously a simple matrix. But now let's watch what happens. This is where it gets really interesting. If I take a doublet, and you remember by a doublet I might mean the electron, neutrino, and the electron. Okay? If I take a doublet and I act on it with this, well, if I start out in the state of the electron neutrino, what do I get when I act on it with this? If I multiply this matrix times this vector, folks, I'm making this easy.
You get half.
Yeah, you get half of what you started with. And if I do this on just an electron, I'll get, thank you. You guys are getting braver and braver as we go. Okay? So what this says is if I am using this gauge boson to mediate an interaction for an electron neutrino, I have an electron neutrino come in and an electron neutrino go out. If instead it's an electron, I have an electron go in and an electron go out. Okay? But now let's consider W mu plus on 1, 0. What do I get? I get nothing. However, what if I act with W mu minus? Any takers? It's 0, 1. I take this matrix and multiply that by vector by it, I get 0, 1. Okay? Similarly, if I do W mu minus on 1, 0, that's going to give me 0, 1. And if I do W minus on 0, 1, it's going to give me 0. Okay? Yes?
Should the first line both have W plus?
Sorry, yeah, that should be plus. Okay? Now are you ready? We're going to have some insight. This thing is taking a neutrino and giving us back a neutrino. It's taking an electron and giving us back an electron. Okay? This thing is taking an electron neutrino and giving me back nothing, but it's taking, oh shoot. No, sorry, yeah, sorry, I get so confused. Sorry, this is it acting on 0, 1.
And then it should be a 1, 0 on the right side.
Oh God, I totally did it backwards. Jeez, thanks for correcting me now after I've already gone through this line. Jesus. Okay, anyway. Yes, all right. So this is taking an electron and turning it into a neutrino. Now here's an important observation. This is taking a negatively charged particle and turning it into a particle with 0 charge. What does that plus mean? That means that this boson has positive electric charge. That electric charge combines with the electric charge of the electron to give me 0 electric charge. Same is true here. The W minus acting on a chargeless neutrino gives me a negatively charged electron. That minus is that this thing has negative electric charge. Okay, you can't do anything in this case. So notice the W3s, the W3 is electrically neutral, whereas W plus minus mu is charged. Okay? Go ahead.
Then why do you get 0?
Well, just,
Put a
it's just,
minus on.
it's just because this boson is not going to interact with an electron.
That just means no interaction.
Yes.
Okay, it doesn't
And
mean
no
it
interaction
made
here.
the- Doesn't mean it made the electron go away.
No, yeah, definitely, yeah, no interaction, okay? So I just want you to notice, we've been talking about that SU2 left rotation thing, but what we've discovered is that the generators that requires, 2 of them come with electric charge. This also means that these 2 generators are going to interact with each other via the electric force, the electromagnetic force. Because they got electromagnetic charge, they can interact with each other via that. Okay? So you see why having the weak interactions period automatically incorporates electromagnetism. Because it's got charged bosons. All right? Okay. Okay, so we've got the neutral, we've got the charge. Now I've got 5 minutes to do my last one. Oh man, Sergio, if you ask me a hard question, I'll kick you out of the room, but go ahead.
Yeah, the easiest is that, what means the negative?
What
It has-
emits the negative?
The negative has some meaning?
Here.
No, in the first row.
Sorry, here?
Yeah, yeah,
That's just a coefficient, don't worry about that. It's not important.
yeah. At the end, I will do it.
At the end of the day, that's gonna have some importance, but not nearly in this interpretation in terms of plus and minus electric charge. That's not gonna be a part of the story. Okay? All right, are you ready, folks? I'm about to hand it to you. You good and ready? All right. Yes. Here we go. We're done with the work. We've actually finished everything. Now I want to make, he's gonna suck that he left. There are two big problems with this. Problem number one, the weak bosons actually all of them. The weak bosons are massive. So the bosons affiliated with the weak interactions are massive. But remember, in the Dirac Lagrangian, if we had included this mass term, this term is not invariant. Okay? So we have a contradiction. We're trying to have this gauge symmetry based on a local gauge invariance, the construction of which requires the masses of the gauge bosons to be 0. Okay? However, experimentally, we detect that these gauge bosons have mass. Therefore, either there's no symmetry argument underlying it, because the symmetry argument leads to 0 mass prediction, but you're seeing a mass, or there's some other fucker that's interfering in the story. I don't know. Okay? All right, second problem. Bigger, way bigger. Remember that, it's gone, I've erased it. But anyway, remember for matter, I'm talking about the stuff we're made of. For matter, mass requires psi left and psi right contributions. Okay? Remember the term is mc squared psi bar left psi right as an example. Well, that's fine though. Matter, matter has mass, most of it does. So you just have the left and the right contributions, right? Make sense? Here's the problem. Before today, all of the symmetry transformations we've talked about, there was no left and right parts of the story. Today, however, there is the left versus the right version of the story. And the left symmetry is different than the right one. The left is SU2 left, the right, the other one is a U1 which acts on both. So my question is this term right here invariant under SU2 left? No, it's not. Because you can fuck around with this, but you can't touch this with SU2 left. So you can take this and transform it into something which is not the same. So for SU2 left to be a good symmetry of the theory, not only do the gauge bosons have to be massless, but every single matter particle must be massless. Well, let's think. How many particles are massless? three neutrinos. Not the electron, the muon, the tauon, the up, down, strange, strong, top, bottom quarks. So we have a problem. It's all about mass. It's all about mass. The Higgs mechanism is going to solve it. Okay? I'm going to go to that next time, but I'm going to finish this lecture with a quick discovery. SU2 left. When we do the Higgs mechanism, I don't think we're going to apply it directly to this example. We'll do a cartoon example because applying it to this is a real headache. So I just want to go over a quick result. This thing has 4 generators, obviously. It's got the W, mu, 3, W plus minus mu, and then we have the B mu for the U1 hypercharge. And then what we're going to do is we're going to take this SU2 left and we're going to break it down to U1 of electromagnetism. Okay? So when we break this down to U1 electromagnetism, we're going to have a single generator and a single associated gauge field corresponding to U1, E and M. And the question is, which of these 4 generators and associated gauge fields might it be? Any takers?
Probably the plus minus one.
Say it again?
Probably the plus minus one. Oh wait, that's 2.
Yeah, this is 2, this is 1, this is 1. So this is for U1 hypercharge, and these are for SU2 left. So which one do you think is going to be the associated gauge field for the electromagnetic U1? Turns out that the gauge field associated with U1 electromagnetism, which is just the photon field, okay? Coming from this story, it's actually going to be A mu is B mu cosine theta W plus omega mu 3 sine theta W. It could only be a combination of this one and this one because these are electrically neutral, and we know photons don't have charge. These can't be part of the story, okay? So the photon field, the gauge field associated with the photon, is just this linear combination of these 2 neutrals. And then it turns out that in the resulting story, we basically have another neutral, which corresponds to minus B mu sine theta W plus omega mu 3 cosine theta W. Okay, so these are just 2 independent linear combinations. The theta W is called the Weinberg angle, and that's the angle which is telling you how much these are mixing. Okay, and then the W plus and minus, they just descend into this story. So what we're going to find when we're doing calculations is that we have the gauge field associated with electromagnetism, we have a neutral gauge field, which is part of this story, but it's not just part of this or this, it's kind of a little bit of both. And then we have the plus and minus gauge fields. The 3 of these are massive. This one is massless. Obviously the photon is massless. Okay? Now, just one last really quick thing. The fact that this had a coupling G prime and this had a coupling G would tell you that these 2 transformations are not unified. There's just 2 separate groups. It turns out G is related to G prime. Okay? In fact, what we can say is that G times sine of theta W is equal to G prime times cosine theta W, which is the coupling of the photon to electric matter. Okay? And then the G in the story is also the coupling to the plus and minus weak bosons, and then GZ is G gamma over sine theta cosine theta. Okay? So all I'm trying to show you is that there was really and truthfully only one underlying coupling in this entire story. That's why we call it a unified force. It's kind of weird because if we write SU2, actually let's do this. Let me say SU3 cross SU2 left cross U1 hypercharge. And I argue this is not part of these forces. This is independent. It's because this has a coupling which is completely unrelated to these couplings. And this group, which although it's a product of two groups, it only has one coupling. So there's really only one underlying interaction. It just has this weird symmetry form. Okay? Yes?
What's the subscript on the last G?
Z. This is the coupling for the Z component. So the G everywhere you see it, and the G prime are the ones that are part of the transformation. And then we have G for the photon is either G sine theta or G prime cosine theta, it doesn't matter. The G for the W plus and minus is just G without any cosine or sine thetas. And then GZ is G gamma over sine theta cosine theta. So look at those for a few minutes and you'll realize what I'm trying to say. Other questions? So once again, these two problems are huge, but they are both going to be solved by the Higgs mechanism. And a critical part of the Higgs mechanism story, which is where this is actually going to be resolved, is the breaking of this to this. Okay, so we're simultaneously going to learn about how to break a symmetry and how to generate the masses for things which are part of the story of broken symmetry. Okay. Talk to you on Thursday about that. Just a reminder, your midterm is next Thursday, and it's going to basically cover the homework. Let me turn the camera off. Hopefully it's on. Oh, it is on.